I welcome all of you again to this second session, second day of FDP, organized by Gauhati University Institute of Science and Technology, Department of ECE. In the second session today, we have with us Dr. Dheeraj Kumar Sinha from IIIT Bhagalpur. He will be delivering a talk on the topic of design of electrostatic discharge protection circuits for high-speed integrated circuits. Dr. Dheeraj Kumar Sinha have done his BTech in 2010 with first division with honors. He has received his PhD degree in the area of VLSI and microelectronics from Indian Institute of Technology, Gauhati in 2017. His research area interests are focused on the development of high current breakdown circuit models and its application in VLSI, such as ESD protection circuits and device to circuit interaction. He was selected in Global Foundries Incorporated Singapore as senior engineer in February 2017. He has worked for 6 months there. He has published various reputed journals in IEEE transactions and in reputed conferences. Since July 2017, he has been working as assistant professor in IIIT Bhagalpur and was the first faculty member to plan, monitor all the activities pertaining to a classroom, hostels, library, land, power on one hand, and put in place academic curriculum, fee structure, academic calendar, etc. Apart from academics, Dr. Sinha is a member of Board of Governors and Senate of IIIT Bhagalpur. He is also holding various administrative positions such as SOD, Department of ECE, Associate Dean, Student Affairs, Director, Secretariat, Media Spokesperson, Student Purses, and Civil, etc. I would like to hand over this session to Dr. Sinha to deliver his talk. Thank you.
Thank you, Coordinator Apurv, and the participants. Good morning to all of you. And today I am delighted that have been invited to this ATAL FDP. And today we will deliver a lecture on a design and optimization of ESD protection devices for high-speed ICs. So, as you know that do you know about the ESD? What is ESD? Have anybody seen this kind of, because have you felt this kind of phenomenon? Anybody? So you can see that ESD stands for electrostatic discharge. Everyone has felt, but I will take example, then you will get to know about this. And why this is the ESD is important in the VLSI, because the VLSI is all about the whatever you develop, it has to be implemented in the silicon. It has to be done. Okay. So to save the IC integrated circuits, whatever you design, you see always you see a pins out of it. When you take IC, you have the pins. Okay. So you want to save the IC. When you touch that IC, you want to save, and that is the ESD protection device we will design to save the whatever the IC you will design, we will save there. So today we will have I will start with the basics of electrostatic discharge, and how we can connect how the typical IC will be looking like, and then we will have the input and output parts, how we can connect over it, what should be the properties of the ESD protection circuit and devices, and when I connect the protection, whatever I design the protection device, and when I connect with the IC, what the problem will be, then what would be the circuit perspective, because here I will take a case where I will take example as the LVDS. You might be knowing about the LVDS. This is a low voltage differential swing circuit. It is used for the transmission of the your signal from the transmitter to the receiver, because you can see that in the IC also you have a transmitter, also you have the receiver. So why we will use the LVDS, and how this performance will degrade when I connect the ESD protection devices, and then what are the device perspectives we can explore, and then I will conclude the session. Okay, so you can see the thing. Have you ever felt this? Whenever you touch the doorknob, this kind of shock, have you felt anytime? Anyone can tell me? Not regularly you have felt, but sometime you have felt. Generally, it happens in the winter days. It happens. If you have not seen, one more example I am giving to you. Uh, why this when the rainy days comes and there is sign of light at that point of time? Why it happens and why it takes place on the heighted tree and a heighted building? Why it takes this process? So you can see that the process depends on the whatever the charge is stored. Charge is stored means when you have the barefooted person, you are walking on the floor. Sometimes your body gets charged, and the body gets charged. That means it range of the kilovolts. 2 kilovolt, 3 kilovolt, it can be. Even it can be 10 kilovolt. It depends on the individuals. Does not depend on only single person that this is the defined value 3 kilovolt. It has to be dependent on the human body that what charge it can store. Whenever you just walk barefooted on the floor and you touch the doorknob is almost having zero charge, and your body is charged up to 3 kilovolt, 4 kilovolt. When you touch the two different things, you can see that one body is charged up to 3 kilovolt, and you are touching a material which is having 0 volt. What will happen in that case? What will happen in this case? What can happen in this case? You can see that discharge will take place because whenever you have a two different potential, when it comes into contact with each other, it can discharge will take place, and you can see the huge amount of charge transfer. Whenever the charge transfer takes place, current will be the major component. You can see that whenever you have the current having a value of 1 to 10 ampere, you can see the shock you will feel there in that case. So this is called the ESD phenomenon, and ESD phenomenon takes place in various cases. You can see that nowadays you can see that when you have the flat apartment, what on the top you can see that the rounded one wire will go from the top of the boundary, top of the floor to the ground. Why they give? They give because whenever the charge transfer takes place from the very high potential to the building, it should not hamper the building, because in the apartment various people will be residing there, and that whenever discharge will take place, all the people will die. That is why they put a rod. A rod will be at the top of the floor, and it will be till the ground of the floor. So that you will see that that phenomenon should not take place. That is the major reason that they put the rod. So this is the electrostatic discharge phenomenon. So you can see that I have taken a thing. You can, when two dissimilar materials are separated and EST charge may develop. That means when you have a two dissimilar materials, one is human hair, you can see one is human hair, one is a doorknob hair. So you can see that there are two different materials, two different charge. So whenever the transfer of electrostatic charge between bodies or surface at different electrostatic potential. So whenever you have two dissimilar materials have a different potential, what you can see that a charge will take place. So you can see that the ESD is a very high current phenomenon. It ranges from the 1 to 10 ampere. Also, you can see that it is very short duration. So this is the major thing that you can see that it is having the very high amplitude but having the short duration. So how you can measure the EST? You can see the what how you can measure. So you always measure in terms of the ampere per nanosecond. So this is the current component and discharges within a nanosecond. So you can see that this is why we are calling that EST phenomenon always measured in terms of the ampere nanosecond. So what are the factors? You can see that these are the factors. What is the magnitude of the static charge? That I told you that human body will have a different charge. So the start what the magnitude it is, and the other materials what is the magnitude it is when it comes into its contact with each other, then it can take place. Then you can see you have the contact quality. That means how did you touch? That means the quality of the touching means you are touching with the soft hand, you are touching with very hard hands. Also, it depends. It depends on and depends on that the EST value will get also change. Also, rate of separation. That means how much time you have touched and thus you've taken out. So it all depends. Depending on this value of the ampere per nanosecond will be dependent. Okay. So why in the VLSI why this phenomenon has come? You can see that, and you can see that the yield. What I hope you know about the yield of the industry. So yield of industry that means nobody tells you, but you can see that once you know the yield means what you have manufactured 100 number of chips. How many number of chip is good? So and you can take the ratio of this. That will be your yield. Okay, so let's suppose 100 chips you have manufactured. Out of this, 20 chips got damaged because of various phenomena. I'm not telling about the only electrostatic discharge. It can take place to the other things also, latch-ups, also electrical overstretch, packaging, testing. There can also be a factor, but EST is a predominant factor where you can see that the most of the IC get damaged because of the EST process. So you can see that when you have visited, I have seen that in the lecture. It is the Tana sir, who is a in the ISRO. What also I visited there, they use the EST straps for what? For because your body also having the same potential will be there. Also, your IC will have also the same potential, so that the EST phenomena should not take place. But even you are handling a IC, you are moving IC from one place to other places. It can take place from anywhere else. So the prominent factor of the failure in the the IC will be the EST phenomenon. Any problem with this? So what are damages? You can see that the damages you can see in the IC when you have just taken the internal parts of this. You can see this is the ESD. ESD means electrostatic discharge. Also, this can damage is the latch up. This is also called the EST. This is electrical overstress. This is EST. This is EST. So how do you distinguish? How do you distinguish between that? This is damage because of the ESD. This is damage because of the latch-up. This is damage because of the electrical overstress. So the major thing is that electrical overstress is taken place having the very higher seconds. That is EST measured in the ampere per nanosecond. However, the electrical overstress will be measured in the ampere millisecond, ampere microsecond. So the time duration of this phenomenon is longer. So that is called the electrical overstress. And latch up, I hope you know about this. The parasitic bipolar inside the device, and that is whenever it turns on, then what can happen? You can see that there also can be a damage in the internal part of the devices, and then you can see effect on the circuit. So EST is a you can differentiate. It will have the time in the nanosecond time. It is in the millisecond time. Larger because of the parasitic bipolar turn on. Okay, and you can see that whenever you have this kind of phenomenon which is in the nanosecond, what you can see that you will have the junction damage. You will see the junction damage and the oxide damage. These are the two major things you will see that Vox. This is the major component. Also, maximum current can stain, and you have the then you will have the oxide breakdown. You will have the junction breakdown. So these two phenomena will take place during the ESD phenomenon, and then we distinguish that this IC is damaged because of this. Okay, so you can see. where it will take place. Where it will take place, image ESC damages to ICs. So you can see that due to IC pulses, the IC chips becomes damaged at the input output signal pin. A failure appears as the thermal damage to the transistor. Thermal damage means what? Whenever you have the very high current, there might be a thermal because you can see that you are first taking breakdown at the junctions. Once you have the junk breakdown, there can also be a temperature increment, heat, joule J heating. I hope you know about this. J dot E heating. Because of this damage takes place. So you can see that where it will be. You can see that it will be on the input and output signal pins. So you must have seen this kind of the IC where you have the various pins, and this is your input output pins. So where there, when the human touches this pin, what can happen? That there might be a discharge. In that case, this phenomenon can take place. So how you can measure? Because everything it is you know that due to this is happening. So what the scientists have done to test this, what they have done is they have developed three kind of model, which is the human handling of the chips. That means human touches the input output pin. That is called the human body model. Okay. Then robotic handling in the assembly. Assembly means what? Where you must have seen manufacturing company where they use various kind of the robotics. All the things are automated. You can see that all the things are automated. Just you have to do a thing. Transport will take place from by the automatic machines only. There also you can see that this kind of the damages can take place. Then you have the charge device model. You can charge device model means we have two ICs. One IC got charged because of anything, and other is not charged. When it comes into each other, there can also be a transfer of charge between the two ICs. In that case, also you can see that charge device the damage can take place, and that is modeled by the charge device model. Simply only thing that you know about this is only charging and discharging I'm talking about. Okay, how you can model this? Simplistic thing is the RC network or RLC network. It is more than enough to model the any of this. So all this will be modeled by the RC or the RLC network, where you can vary the rise time and fall time of this, rise and fall time of this. So you can see this is the human body model. You can see this is a human body model. You can see the picture. This picture you can see what you are getting from this. The human would like to touch. Human would like to touch the IC. That is pin. You can see that the pin. You can see they would like to touch. But what happens? Touching is not the major issue, but when the body gets charged, then you touch that IC pin, input output pin. What can happen is their damage will take place. So you can see that how we have modeled this human body model. Only you have the capacitor. This is your resistor. Resistor will have the value of the 1.5K. Capacitor will have the 100 picofarad. And this is your device under test. Now you can see that ESD takes place not at all, not every time. During the normal operation, this ESD phenomenon will not take place. This phenomenon will take place. What can happen is the normal operation should stop, and this ESD phenomenon should be overcome. So you can see that there is a switch. What will happen when, let's suppose it is a 1 kilovolt is a charge in this, and you first, when the normal phenomenon is taking place, you can see that all the capacitor, all the voltage will be charged in this, and whenever the ESD phenomenon takes place, the charge will take place under the device under test. So this is your human body model for testing a IC. So you can also develop at your home also, because this is a simplistic model you can use for the testing the IC, that how much value it can sustain, how much value this IC can sustain, and after this get damaged. Okay, so you can see that mimics the human touching of the device under test. That means that we have given that how we can touch the IC. Voltage could be as high as 10 kilovolts. So you can see the range of this could be the 3 kilovolt to the 10 kilovolt. So depending on the person that how much the person got charged because of the phenomenon, EST phenomenon. Then you have the EST model by the series resistance RB equal to 1.5 kilo that I have given to you, 1.5 kilo ohm. Also you have the 100 picofarad. Okay, so this is your human body model. Also we have other two models also. The machine model. Machine model, what I have told that whenever a transport will take place, because everything is automated in the industry, I don't have to carry from one place to other place by the human. Everything is automated. Just you keep the IC here, it will go to the other place where they would like to have. So you can see that this is your conductive path, and this is your thing is there. And when it comes to whenever it is revolving, what will happen that this metal can also charge. It can charge up to the what 0.5 kilovolt, and your IC there when it comes into contact with each other, what can see that there also can be a damage, and the equivalent model is the simplistic LC. LC. This is the this is the your inductance, your capacitance. Again, the same thing will take place whenever the EST phenomenon takes place. This path will be open and the conduction will be there. So you can see that 100 to 500 volt amplitude will be there. Capacitance will be like this. This is your 0.5 micro or 0.5 microhenry. This is your thing. Then you have the charge device model. You can see that charge. What I told that when your two charge devices are charged and comes into contact with each other, then also can be a damage. You can this is your picture of this how it can take place and how we can model with the simple RC circuit. And you can see that this is your thing, and this is your total. They all depends on the capacitor value here. Okay, so this is your thing. So you can see that the amplitude, this is picture is not clear to you, but you can see that this is in the amperes, this is in the time. Okay, so you can see that this is your for the this is your for sorry for this. So this is for, you can see that this is your HBM characteristics, this is your machine model characteristic, this is your charge device model characteristics. When you test this, what you can see that the very dangerous phenomenon is the charge device model. Human body model is the initially in the range of the nanosecond, but discharging takes place at very slow speed. Okay, machine model is little bit faster discharging, but you can say discharge of the machine model is very much rapid. So you have to overcome by the CDM is the major prominent thing in the industry because nobody can overcome by this. So you have to use the EST, you have to design the EST IO pads so that your IC can be cannot be damaged. That is why the EST protection device is very much important, and you have to connect at the what you have to connect the input output pin of the IC. Okay, so this is the thing. So you can see that how we can do in the when you are working in the industry, how you can test that how much value it can sustain and how much thing it can sustain. So you can see the industry two thing can be used. One is the HPM, CDM testers. You can see that this is your tester. You can see from the in the industry. This is the picture. So you can see this is your the tester will be there, and you can put your here. There are also option for the device under test. You put your device and you can test the HBM model. You can test the HMM model. You can test the CDM model, and then you can see that this device can sustain up to what value. That means that is what value means what maximum ampere per nanosecond value it can sustain, and result will be your pass or fail. That means if you apply at 2 ampere per nanosecond, it is sustaining or not. You have to test it is 4 ampere per nanosecond, it is sustaining or not. if you apply a 5 ampere nanosecond, if it is failing, then you can tell that this device can get damaged after this value. So that is a test you can operate in the experiment labs also. But better thing we have seen that a TLP tester is more very much useful. Why you can see that in this, that you have this setup, so you can also measure the IV characteristics. So how the IV characteristic of ESD protection device, I hope anybody has seen or not. This kind of IV characteristic will be there. S-shaped kind of IV characteristic for the ESD protection devices will be there. And this is non-destructive, means even the high ampere current is higher, this will not get damaged. However, when you have the higher amplitude of this device can get damaged. So in the industry, what they use that they use the TLP tester at their home, that their manufacturing company, and you can see that you can use the TLP tester for this purpose. Now coming to that I told you that this is your IC, where you can see that I told that EST phenomena will take place at the input output pin, and there are four modes of the jappings. That means four modes of the EST. First is the PS mode. PS mode means paused. Ah, any question? Any question? No. So you can see the PS mode is the positive EST with respect to VSS. That means what? This is the EST phenomenon, but taking with respect to what? The lowest supply voltage. This is the VSS. So VEST, that means this is the positive slope. This kind of phenomenon will take place. This is the ampere, and this is your time. So this is your PS mode. That means positive EST with respect to VSS. Also, you have the NS mode, negative VST with the respect to VSS. So you can see that in the japping mode also you have two options: positive VST with respect to the VD PD mode, and the negative VST with respect to the VD mode. So when you test in a TLP tester, all these modes you have to operate and measure that what the maximum amplitude it can sustain. That is your thing only. Okay. So these are the things in the experiment side of thing. Now we will come for this. So you can see that how we can do that. That is the testing thing we have covered. When I started with the EST phenomenon, how it is impacting the VLSI industry, then how they test the whatever the IC they design, they put a EST pad at every input output pin. They need to test. They need to test means what they can test using the TLP tester, and also you have the four option: PS mode, NS mode, PD mode, and the ND mode. That mode will be there, and then you can see that. But which when you are connecting a device at every pin, input output pin, which kind of the device you will use? A major question is which kind of device you will use for that purpose. So when you are operating, when you are taking this, there are two kind of the protection device may be used. One is the snapback protection devices, and other is the non-snapback protection devices can be used. Okay, so snapback protection devices, where we can do that? We can do in that case where you have the NS mode, that means PS mode will be there and the NS mode will be there. Then you can see that we can use, and you can, this is the snapback devices we can use at this place. That means I will discuss because more about this snapback device, that where we have to connect this, and when we connect this, what should be the properties of this snapback protection device, that we will discuss in this thing. So also you have the non-snapback device. Nothing is there. You have to use the one. Both are reverse. One is the forward bias diode. One is the reverse bias diode. No, this is the sorry. This both the reverse diode we will use. Why reverse bias diode we will use here in this case? Why reverse bias diode? Reverse bias diode, that means it will not turn off value, turn off at 0.7 volt. It will turn off at the breakdown voltages. Okay, that is why we are using the reverse bias diodes. So whenever you are talking about the non-snapback devices, you can see that you can only use the reverse bias diode. Sometimes the scientists have used the bipolar transistors. So you can also use the bipolar transistor for this purpose. Okay, but at this also has to be used in the that the NPN has to be turned off. NPN has to be turned on when you have the higher current amplitude will coming into picture. So we will discuss in detail about the protection device because the major thing what they can do that they can optimize the circuit because you can this is your main circuit and main circuit you are at this is your reverse bias diode and one more thing you are adding here this is a snapback protection device. So why we are adding this? This is a major thing why we are adding this and how we can overcome this ESD phenomenon. So this is thing here also you can see that this is your diode in the reverse patch we have connected and also you can see that one more device we will use with the snapback protection devices which will surely tell you that it cannot damage because of the ESD phenomenon. But this ESD protection has some properties that we will discuss. Okay. So this is your typical IC and iPads. This is your ICs. This is your internal the layout part you will see. This is your thing you can look like. So this is your input output pin. The pin you have seen here. This is your AST protection device. This is your AST protection device. You can connect a snapback device here. You can connect the non-snapback device here. Okay. This is your internal circuit. Now you tell me that when this circuit will come into picture, when this circuit will come into picture, and is any problem will, during the normal operation, what will happen in that case? Will this will turn on during normal operation? It will be turning on or not? And during the normal operation, what will happen for the IC? And during the EST phenomenon, what the problem will be the IC. So one by one, I'm telling you, during the normal operation, the first property of the EST protection device is that during the normal operation, this EST protection device should be off. Normal means what? That whatever the function you want to have, operating a function, it should give the results. So there should not be a disturbance in the your normal operation of the IC. But also one more thing, there should not be impact of the ESD protection device on the internal circuit. Second thing, that you don't your ESD protection device should be designed in such a way that this should not impact on the internal IC. What impact I'm talking about? I'm talking about the noise because when you are applying a signal at this input pin, because of this some noise can also come and due to this what will happen whatever the signal you are sending from one place to from here to here there might be a noise even this is off but there is a noise because of what because of the leakage current there might be a noise and they can harm the normal operation of the internal circuit. So you can write here somewhere during normal ESG protection device would be off. Okay. Second is during normal operation, ESG protection device should be off and it should not add noise in the signal. Okay, so during normal operation, simple thing that nothing should be there. Two things has to be overcome. It should not be on during normal operation. It should be off. Second thing that no noise should be added in the your signal which you are applying at the input output pin. These two things. Now, what will happen during the EST phenomenon? during the EST phenomenon, what will happen in that case, whatever EST phenomenon takes place at the input output pin, it should get tie up with this EST protection device circuits. It should be dire. No impact should no EST phenomenon current should go into the internal circuitry part. So during the EST, you can you can see that all the current should pass through this path or this path. So what will have why we have connected this? You can see that this is a parallel connection. This is your parallel connection between the internal circuit and the EST protection device. What will happen that when this takes place, it has to be go through this path. That means the resistance R on resistance of the EST protection device has to be as minimum as possible. So during the EST phenomenon, the device should turn on. The protection device should turn on. First thing, you can see that during the EST phenomenon, the protection device should turn on. Second thing, turn on means what? That as soon as the EST phenomenon comes, it should turn on so that no damage can take place in the internal circuit. So the R on of the EST devices has to be approximately equal to 0. That means, let's suppose it has a 1 kilo ohm value, this resistance value, it has to be as 1 ohm to 10 ohm kind of thing or 100 ohm kind of thing will be there. So that all the current should pass through this path, should not go to the internal circuitry. So I hope it is clear to you that when you connect the ESC protection device, that it will not harm the internal circuitry operations, but it will try to manage the EST phenomenon. So this is the two things. So you can see that this is your input output interconnection. So you can see that you have to communicate with the ICs between ICs. You can see that when you have the chips, you might have seen chips. Inside the chips, various function modalities will be there, and there is also a communication between one block to the other blocks. So the transmission of the signal will take place from the one place to the other place. So you can see that they also are. You can see that there also have IC number one. This is your IC number two. In between, you have the transmission line. You have the transmission line. So you can see that what will be the problem, because you have connected your EST IO pads uh, to the input output pin of the IC1 also. You have connected at the input output pin of the IC2 also. What the problem will be in that case? Hmm? Any problem you can see in that case? That you can see this, you are applying a signal here, you are taking output a signal here, but in between you are processing between the two IC, and you have the transmission line. Also you have at each input output pin you have the EST pad. So you can see that there must be a synchronization between the IC1 and IC2. Should be, because you can see that I hope you have taken the you know about the EMT, electromagnetic theory. There is a impedance matching. I hope you know about impedance matching between the two transmitter and the receiver. If you want to have the very good transmitter, if you want to have the zero loss, what you can see that the impedance value has to be as approximately equal to 100 ohm or 50 ohm. The value is that impedance matching in that case. So the transmission line should have this kind of thing. So you can see that you have connected a EST pad here, and you have connected EST pad at this place. So both you can see that here the 50 ohm or 100 ohm, whatever the impedance matching is required, That thing has to be done. So you have to have design a ESD pad. It should have the resistance value approximately 150 to 100. You can keep in between here to 50 to 100 ohm. Also, you can see the various constraint. You can see the one constraint is that where there you can see that a device should turn on at this time, device should turn off at this time. What should be the order value? All these things has to be there. So you can see that this is your transmitter, this is your receiver. In between you have the transmission line. So you can see that you see pad capacitance here, transmission line here. Here you have the load resistance and the bond pad capacitance. So you can see the issues that the interconnection issues you can see in these cases. Okay, so you can see that circuit to device interaction. That means when you connect circuit with the device. Okay, because in the transmitter side, what is the problem is the circuit to device interaction. What can happen is that there may be a false ringing of the device. That means sometimes they can feel that the ESD phenomenon is coming. Sometimes the false ringing can be there. Additional ESD current path during a stress. That means you are connecting a IC with this. This is a parallel connection. Sometimes some current can also go to the IC. Also, you can see the signal corruption or circuit malfunction because you can see that because of the noise it can take place. Okay. Now, device to circuit interaction. What are the issues? Circuit input output impedance mismatch because you can see that from the transmitter from the receiver you have to have the perfect matching. The output impedance mismatch may be there. Delay is also one of the factor. You can see the ESD and the CST because when you are whenever you are designing a device, there must be a you are not wanting to have the this kind of the resistance and capacitance, but the parasitic resistance and capacitance may be there. So there may be a delay because you can see the when you apply a signal at the input output pin, there might be a delay because of this ESD protection device. So these are the issues we have, and these issues has not been resolved till now. So if anybody would like to have that research on this, you can do that. Okay, to resolve the issues. Here I have taken an example because you can see that I told that PhD protection device has to be used in the circuit, and topic is the high speed IC. High speed IC, that means you can see that this is the high speed IC. This is one of the example of this. This is LVDS. This is low voltage differential swing device. That means low voltage differential swing. That means what? That IC will operate on the low voltage. That means on the voltage of the 0.9 volt, 1.8 volt, depending on technology. That on what technology you have designed this. Let's suppose you are operating at the 90 nanometer. You are taking 1.8 volt or 0.9 volt. So this is your circuit design point of view that what technology you are using, and depending on that, you have a supply voltage. At that supply voltage you should work on. So LVD is very important component of a IC where it can operate on the low voltage. Second thing is the volt differential swing. There is two kind of a swing might be there, single ended and double differential ended. So what the problem with the single ended and why we prefer to have the differential swing? That means you can see that when you want to transmit from transmitter to receiver, this is TX, this is your RX. When you have a single ended, what you can see that this is your thing, and you have the supply maximum voltage with supply voltage. Because of this, what you can see that a noise can come at the transmitter side. Okay, but this noise cannot be suppressed now because this noise, once it comes into picture, it will go to the receiver side and it will have a distortion in the signal. However, when you take a differential swing, what will happen? You have the complementary thing. You can see that you have, this is your complementary thing you will apply here. So what here also you will see the noise. What you can see that you can cancel the noise when you take the differential swing. So differential swing has some advantages. So you can take that. You can use a differential swing for the IC, and it can operate at the lower voltage. So you can see that I have taken LVD as an example for the high speed IC. So here also you can see that I told you that different type of transmission line will be there. So single ended, some problem is there. There is also single ended, problem is there. Differential and single, sometimes it can give, sometimes it does not give, depending on requirement. But LVDS is a differential ended. Also you can see that why we use the LVDS. Also we have the option of the CML and the ECL because of this advantage with the power consumption. You can see that very lowest power consumption you can see, and you can see that at very low voltage it can operate, and you can see that the impedance matching of 100 ohm you are getting here. Also you can see the speed, 2 GB speed. So if you want to transfer data from at the rate of the 2 GPS, you can operate it. Also the distance we have taken, you can take a distance 10 meter. So you can see that over the CML, and CML LVD has the various advantages. You can see the power advantage. You can see the operating voltage advantage. Load is not a problem here. Here speed is higher because of what? Because we have the lower distance. So LVDS may be used for that purpose. Okay. So how the block diagram will look like, and how you can test. So when you want to do that research on this, if you have this cadence, or somebody has a mentor, they can use this. What they can do that on the mentor, on the LVDS, on the cadence, they can design the LVDS for a given technology. Let's suppose you have the 45 nanometer technology library is there. You can design that LVDS. So how you can connect? This is the block diagram of the LVDS. The two output will be there. You can see that also at the, you want to have the load resistance at the 100 ohm, and this is your transmission line. This is your ESD protection device. So part A, how will you perform this? How you can design this circuit on the cadence augmenter, design that. What you can do that, you have to use the library of the ESD pad. So there also you have the ESD pad library. Okay, you connect this. Once you see the result without connecting the ESD pad, what is the output we are getting there. And when you connect with the ESD pad, how we can get the what the detonation will take place, that you see there. So you will see that when you scale the technology of this, you will have the various impact of the ESD pad on this LVDS. So why this? Because you can see that this LVDS is being operated at a 2 Gbps, but your EST pad, what they are doing, that it is not operating at this voltage, because it has to be turned on faster than this LVDS. You can see what I told that EST pad has to be at very high speed, because it is 2 Gbps, it has to be done earlier than this. Okay, so this protection device is a challenge, that how we can design a protection device, because when the scaling will take place of this protection device, there a lot of the problem, the reliability problem will take place there. So this is the second work problem. Third is that you have to use the differential twisted cable, and you have to have the load resistance of the 100 ohms. Okay, so these are the things you have. So part A is I will just discuss about the how the internal circuit of the LVDS. Part B, we will discuss how the EST pad will look like, and how we can design this EST pad. We will see there. Part C will not look at much, because this is most of the things from the electromagnetic theory, that how we can design this differential twisted pair. But we'll try to have the various load resistance we'll try to put there and we'll see the performance on the LVDS that we'll see in this case. So you can see here that this is the LVDS part. LVDS part means you can see that. Have you seen this kind of circuit? Have you seen this kind of circuit? Anyone? Or anyone can design this on the cadence? Anyone can design or not on cadence? What I have done is that I have the design on the cadence. Uh, so somebody can also design on the mentor or some channel can also be used because these are the EDA tools which can be used for the circuit simulations. So you can use this. And the library I have used for this purpose, which is the 180 nanometer library, which is the SCL Chandigarh that we have know about this. SCL ISRO lab is there. Library we have used from the ISRO. Okay. So what you can see in this case, you can see that this is your differential mode. You can see that whenever this is your one output taking place at this point of time and other is taking at this point of time. What you are taking output, you are taking output. One output you will see like this, other output you will see like this. That means that complementary in the nature. You can bipolar means one is the on this like this, other will be like this. Okay, and second part will be that you have to use the ESD pads, and this is a transmission line. This is your thing. So you can see that how it works. You can this is your current source. So nothing comes free. You have to use with the MOSFET. You have to design the current source. It is handling a current of the 3.5 milliampere. This is what. This is what. This is also a current source because you can see this is on the top. This is your. You have to. This is source. This is your same. So in between you have the differential voltage circuit where you can see that the output will be taken at that point of time, at this point of time, and this kind of output you will see. And it has to pass through what? EST output pad, input output junction, has to pass through that, and you can see that this EST pass not disturb the whatever the input it has at this point and at this point so you have to use this design this EST pad. So this part you can design on cadence. This pad you have to use the library of the SCL where you can see that you can use the layout. You have might have seen the layout of this EST pad where you can see that they are using the gate grounded NMOS. This is also NMOS, but this is not gate grounded. Okay, so we'll see that how this ESG pad will look like, and then the complete solution we will see. So you can see that two things. You can see that result of this when the ESG pad having the capacitance of the 200 picofarad. How you can see that your result is very much smooth. You can see that this is your this kind of result you see, and this is your called the eye diagram. That means whenever the differential swing, what you can see that you can have the this kind of thing. This is your eye opening values. Okay, so you can see that when you have the very high capacitance, EST pad capacitance, what you can see that you have a perfect eye opening in the output. But when you have used the very lowest pad capacitance, what we have seen that we have very much deterioration in the output, and you cannot distinguish that what the output I'm going to get here because the nothing because twisted all the thing has got messy. So we want to have this kind of the result. You don't want to have this kind of result. From this, what you can see that you have to keep your ESG protection device approximately 100 to 200 picofarad. You cannot keep as low as possible. So you have to use a higher value of the pad capacitance. So one thing you have taken care from the performance. So you can see that eye opening height that I told you that this is your eye opening height. This is your eye opening height. Okay. What I have to, I we have been I have done we have done this. What I have varied with the what we have varied with the, so you can see that varied with the EST pad capacity. So what you can see that when this is your value, you can see 10 to the power 0 to 10 to the power 1, 10 to the power 200 picofarad, 1000 picofarad, and you can see that after that the eye opening will be 0. The degradation will take place after 1000 picofarad, the degradation has taken place. So you can see that you have to use a picofarad, which is you can see that 1 picofarad to the 1000. This is your height diagram. Okay, and you can see that the time I rise time, fall time I bit, and the data bit also we have changed with the pad capacitance. So I diagram the pad capacitance which we have connected here. You can see at this point, you can the pad capacitance which we have connected at this point, we have connected at this point. What you can see that this EST pad has capacitance has to be higher than 200 picofarad. Then we are getting a very high value of the eye opening, a very good rise time, fall time, everything we are getting there. So we try to have EST pad capacitance as high as possible. Okay. So now coming to that constraint we have taken from this, the pad capacitance has to be higher. Okay, that thing we have taken from the that. So you can see that what should be the properties of the ESD protection devices, because we have taken the case of the circuit LVDS we have taken care, and we have seen that when I design a LVDS, what we have seen that when I connect with the ESD protection devices, there is a degradation in the output. So what you can see that you have designed a ESD protection device, we should have the capacitance having the higher value than the 200 picofarad. So that is the thing from the circuit point of view. Now, but basic thing which we have discussed about what we have discussed that in the initial thing during the normal operation how it should work during the EST phenomenon how it should work. So you can see that it should act as an ideal switch parallel with the node to be protected. That means you have must have seen that this is your IC, and we have connected a pad here, and also we have connected pad here. What is that? You can see this is parallel with the this. So you have to connect the AC protection device has to be in the parallel with the device under test. Then you have the high current handling capability. That means I will still know about that. There will be IIT terms, maximum current handling capability will discuss. Okay. And you have a low impedance state during the AC phenomenon. What we have discussed that when you have a parallel thing, wherever the lowest resistance will be there, current will go to that part. So this AC part has to be the very low impedance at when the AC phenomenon will take place. Also, it should turn on very fast, less than 1 nanosecond that you would like to have. Okay. So also it should act as a driver because it has to be connected at the input output pin. Protection circuits are implemented in the safe operating area. So what is safe operating area? So you can now see that this is your IV characteristic of the ESG protection device. So what you can see that you can see that this is your A-shaped kind of the IV characteristic, and you can see that there are four regions. You can see that this is your first region, this is your second region, this is your third region, this is your fourth region. Okay, and your device has to be operated in the which region? That has to be operated in the fourth region. Okay, that means what? You can see that during the normal IC operation, the current should be zero. Okay, in this the current can sometimes it can rise there, and but it should not the voltage the VT1 here the term is a VT1 and the IT1 voltage at this turning point should be lower than the oxide voltage, the gate oxide breakdown or the junction breakdown region. So that voltage has to be lower than this. The VT1 has to be lower than the, you can write here, VT1 has to be lower than the oxide voltage. Okay. Then this holding value, this VH is what? Holding value, that means when it has snapped back, it should not go to the normal operation. It has to again switch on. You can see that, you can see that this is your, you can go here. Okay, so the voltage value should not be lower than the normal voltage. You can write here, this is the VDD value, supply voltage. So the VH has to be higher than the VDD. Okay, then you have the highest voltage and the highest current. This is your IT2, this is your maximum current capability. That means no device can operate at the infinite current. You can must see that. And the device has to have some reason, and nothing, no device get damaged because of the voltage. Most of the device get damaged because of the maximum current flow through that device. So when you take a resistor, they also resistor also get damaged sometimes whenever you have the high current flow towards the resistor. So there is a maximum current capability, and that is the RT2. Okay, so this is your ESD design window. Okay, and after that, what you can see that the more the thermal breakdown means whenever the J dot E Joule heating takes place, there because the maximum current will flow and the device get burnt out. So that device has to be lower current capability lower than the IT2. So these are the things you can see that VT1 has to be lower than V oxide. Second thing that V holding should be lesser than the supply voltage. And then you have the maximum current handling capability. Current capability. Okay. So you can see that fast trading time during ESD stress, high current handling capability, and least ESD circuit interaction should be there. That I had told that I have taken the case of the LVDS, and you have seen that some impact will take place and your eye diagram got obstructed. So these are the things you have to see. So you have what you can see that what is challenges in designing, because you will get the result. There is no problem when you do simulation with the TCAD. So I have done the simulation of the ESD protection device, the gate grounded NMOS device we have used for this purpose. You can also use the SCR can also be used for this purpose. Okay. So you can see that what is the problem? Problem is very major problem. You can see that the IC is getting a scaling up to the 3 nanometer it has reached, but the ESD protection device is not able to scale that much. Okay, why you can see that when you want to scale the technology, you can see that it's your technology 0.5 micrometer, 0.35 micrometer, 0.25 micrometer, 0.18 micrometer, 0.13, 0.9. This is kind of a scaling is taking place. What you can see that this is your oxide breakdown curve. This is your maximum supply voltage. Supply. What you have seen that as technology is getting shrink, supply voltage also getting a scale. Also, the oxide voltage is getting a scale. You can see that the range. You can see that the range of this is getting smaller and smaller. That is what The ESD, that this ESD design window at higher technology, you will see like this. As you scale, you will see like this. As you scale, you will see like this. So you have the very narrow ESD design window to design this. Okay, so this is a major challenge because when you want to scale the ESD protection device, there may be a major problem. Okay. So you can, if you want to have research, you can do research on the design of UHD protection device for the current scale technology, which is the 3 nanometer, 5 nanometer, 9 nanometer, whatever you want to choose. But when you do that, you can also use the FinFET. You can use the FinFET for this purpose because nowadays FinFET is being used in the ICs. So you can use the FinFET for this purpose for the AC production, the other AC production device. So you can work on it. Okay. So you can see that the thing which we have written here, background voltage of CMOS device is decreasing. Traditional ESG structure not a scaling with the technology scaling. The major problem is there. It is there. You can write down larger uracil metallization cellular junction. That means metallize the oxide breakdown is also there. You can see that earlier we were using the silicon dioxide. Now we are using the hafnium oxide. So also the junction breakdowns and the oxide breakdown will take place. So increasingly difficult to provide low impedance and low capacitance discharging power. So this is a major challenge. But in my PhD and my research, what we would like to have that as low as the low impedance, as the low capacitance charging path. You can also try various device. I use the GGNMOS. Now I'm moving towards the other device also for this purpose. So the major device when I started this research on this, it was the NMOS only. NMOS is what? Gate grounded NMOS. You can also use the SCR. You can use the SCR. You can use the SCR. You can use the diode. You can use the BJT. Diode and BJT can be used for the non-snapback device, and no problem with that. You can use that because that is the major thing always you have to use. But before that, for more device, you have to use the snapback device. So NMOS and the SCR will have the IV characteristic of the S-shaped kind of IV characteristic. Not a snapback means what? That means what? You can see that I'm talking about the not a snapback. So you can see that SCR and NMOS will have this kind of the characteristic. But the BJT and this, you can see that this kind of characteristic in the reverse breakdown cases. Okay, so it does not have the snapback. A snapback means it has gone to this voltage and it has a snap to the holding voltage. So this is the snapback device, but this device does not possess the snapback behavior. So you can use the NMOS, you can use the SCR. Almost also you can have the NMOS. You have two types: GGNMOS, GCNMOS. Gate grounded NMOS and the gate coupled NMOS also can be used. Sometimes also we can combine the NMOS with SCR for this purpose. Various articles you can see on this topic. You can do that. So you can see that how the research has progressed and we have reached to 2020 and we have seen that various processes, DNMOS, PDNMOS, guard ring, multi-finger, substrate triggered, embedded SCR, various kind of techniques we have used to for this given device. That how we can protect the internal ICs because of the CHD. So this what I have done is the GGNMOS we have used, and we have used the multi-finger technique. Also, we have used the waffle layout we have used in this case. So you can see how you can check ESD, how you can check the ESD. So you have to have a device and what you can see that initial selection of the ESD structure, that which device you are going to use. So you have to use the device, and then you have to use the process simulation. Okay, and then you have to see that how the IV characteristic look like. This is the S-shape kind of knot. This is within the AST design window or not, that you have to see. Okay, then this is your within the range or not, or the within the thing or not. You have to see that. If it is not there, then you have to again restart. Okay, so when it passed with the ESG protection device, what you can see that you can use in the IC that it is working properly or not. So you can see that it is the hit and trial method you have to use in this case. That first you have to use your ESG protection device. This is in design window or not. Once it is design window, what you can see that you can use in the mixed mode simulation or the cadence simulation. Use that device and use. You can see that this is impacting the performance of the circuit or not. If it is not impacting, then that design is very good. Okay, so they are the steps where you can use for this purpose. So how you can, because you can see that you are using a EST pad. Okay, EST pad, how you can extend the information, the device information is very, because industry will never give the device information to you. So you have to be smart. You have to be the what you can do that you have to be the this engineer kind of thing. So what I have done, I have taken the EST part from the library of the UCL Chandigarh. I have extracted the reverse engineering I have done. Okay, because the layout is given to you, and from the layout you have to get the information of the device. Okay, so what are the information I have? You can see in the layout, which is the oxide thickness, substrate doping, junction width, drain to source width, let me spacing of this, and the mobility of the that given device. So these are the properties of the BCM spice model, where you can connect and then you can extract the device information. Once you got the device information, you can design a device certificate, you can get the result of this, and you see that compare that means this is within the design window or not. If yes, you go there, device ready for the solution, and you can see that you can use the, so I have used the NMOS for this purpose, and you can see that you have the NMOS like this, you can see. So this is the device information you can gather from the layout of the IST pad. So you have to what we are doing is that we are doing a layout optimization for the circuit point of view, because the layout is given of the AST pad. We have to optimize for the given circuit. And nowadays, when you go for the industry, for every design of IC, you have to design a separate EST protection device. So you have to use that thing, the pro I have given to you, and these are the major thing you can use in the industry, which is the device structure optimization and the device layout optimization. Okay, these are the things you can do that. Okay, so device layout optimization, how you can perform that? Yeah, we can gather the device information and how you can optimize the device layout optimization. So when you have the layout, you can calibrate the ESG process simulation in your TCAD. You have to use the meshing of this, and then you have to characterize the HBA model, AV model, CDA model. You can use that. You compare this, and within the parasitics, that means the ESG capacitance is within the limit or not. The limit you can use that. So this layout optimization can also be used for this purpose. Device optimization can also be used for this purpose. So in the layout variation, what we have been that we have used a multi-finger. I have changed. We have changed the drain to gate spacing, gate to source spacing, substrate to source to drain. Also, we have the multi-finger and the guarding. So these are the techniques I have used to optimize the EST protection device for a given LVDS. So you can take any test circuit from your point of view. You can take any high-speed interior circuit and you try to use the EST protection device connection. You see the impact When you see the impact, you can see that there is some degradation. So you see, you measure the EST capacitance. First thing, once you measure the EST capacitance, you will get to know that this is the range of the EST capacitance. Then you go to the layout optimization. These are the techniques you can use. You can see that I have used these things. You can also use a different things for this purpose. So what we have seen that we have seen the length, width, multi-finger thing, yes, gain to get spacing, and the uh, BS is the what subject to source and drain space. Okay, so you can see the what impact on the this yes, design window. We can see that this is a major component. VT1, VH, holding voltage, IT2, R on, and the CEST. R on is what? R on we have not discussed here. R on is this is your ROM. That means this is your ROM means voltage by current. So you can see the ROM. So what because at different you will see this kind of result also you will see in the your protection when you design the product device in the logistic card. So you can see that uh, BT1, BH, IT2, ROM, and the CHT. So what you can see, this is your increasing, this is your decreasing, so this is increasing, this is decreasing, this is constant. So what we have changed that when I have changed the length of the, when I have changed the length of the what device, what you can see that, you can see that, you see your VT1 is increasing, holding voltage also increasing. So it will have some impact. So length we cannot change here. EST capacity also getting increased. Width, what we have seen the width, when I change the width, IT2 current is decreasing. That means when you increase the width of a device, your current handling capability will be higher. Also, your R-on will be lower. That means also it is much of the requirement. F is what multi-finger. When you increase the multi-finger, no impact on the VT1, no impact on voltage, but I22 will get increase. Also, that you can use the instead of increasing the width of the device, you can use the multi-finger of the device. You will have the higher value of the IT2. Also, you will see the higher value of R1. This will be your constant. Drain to get spacing, no impact on VT1, no impact on VH, only impact on IT2. So you can see that no impact on R1 and you have the ESD. So drain to get a spacing, what I had observed in my thing, that drain to get a spacing is major thing. Uh, When I change this, I have got the better performance in the IC. Okay, so in my case you can use a different when you do simulation you have the different thing. You can see that sometimes you use the AF, you have the better performance for a given circuit. Okay, so in my case what I had seen that drain to gate spacing has improved the performance of the LVDS. Okay, so you can have the different techniques for this purpose. So drain to get a spacing means what? Drain to get a spacing. Because you can see this is your mouse. Drain to get a spacing. This is your to drain to get a spacing. That means you can see that there is a separation of this. This is your thing. Drain to get a spacing means what I am just not able to draw this. So this is your. So you can see that your drain is there, gate at this point, so it is the your drain to gate spacing, this range. Okay, so the drain to gate spacing, when I just increase the drain to gate spacing, I have got the improved performance. So you can also try that. And what performance I have obtained, that IT2 is remarkably increasing, that the current handling capability of a device has significantly increased. R1 is constant. ESD also is increasing higher than a 200 picofarad. That is the measurement of the given circuit. Okay, so you can see that once we have fix it up this, what we have seen that this is your IV statistic. We have done simulation of this AC protection devices, and this is your thing we have got. And what we have seen that drain to get a spacing, and you see it is 0. once I increase 0.2 micrometer, I have got the improved IT2 at this point of time. Okay. So also you can see that IT2 is increasing current handling capability, increasing with the increased drain to gate spacing, but after 0.3 it is getting a constant. So after 0.3 volt, 0.3 micrometer does not impact that much on the circuit. So now coming to the multi-finger and DCGS, when I change the multi-finger also DCGS because DCGS is the major thing I have found out from this. So you can see that multi-finger, it is 1, 2, 3, 4, 5 multi-finger we have used, and DCGS also width we have increased up to the 2.5, and this is your capacitance we have obtained. Okay. You can see the pad capacitance DCGS. So you can see that this is your pad capacitance we are getting here. Okay, 250 picofarad we have got here. That is a more than okay for this for my given LVDS. Similarly, for this we have done this. Also, I had tried to have that how the thermal variation is taking place inside the design GGNMOS. We have seen that these are the thermal variation we have seen on this device. Okay, so these are the things we can see that summary we can see the target is that whenever you design a ESC protection device, target has to be first target has to be that current voltage characteristic has to be within the design window for a given technology. So let's suppose you are designing a protection device for 45 nanometer, that has to be a in the design window of this, like this you have to have. Okay, first thing, IT2 has to be as high as possible. That means this value has to be as high as possible. CAST has to be not very high, not minimum, in between 200 picofarad to 1000 picofarad. Okay, turn on time should be very much minimum, ranging of the nanosecond time because it should be turned on for the high speed circuit. It should be very much lesser in the nanosecond picosecond. Okay, so you have to take this constraint EST device design. You can take a constraint of the channel length. You can take a DCGS. You can take a constraint of the channel width. Okay. So what you will see that what will be the maximum device width you can see here, maximum allowed CST and the core input output circuit design. So these are the things you can perform. So what would be the conclusion of this topic? It will be EST remains a major cause of chip failure because you can see that the scaling of the CST pad is very much difficult because of the this design window. Okay, and when you want to have lower design window, other thing also getting up because of EST capacitance, add-on capacitance, add-on resistance will get turned on, or the impact of the circuit, impact of device or circuit will take place. So these are things. So ESD affects entire manufacturing from device to system because once you are not having robustness of this ESD protection device is not there, your system will not work properly. You will have the yield will be lesser and lesser for the industry. Significant challenge for nanometric technology. So you have to when you have the nanometric technology, this kind of the thing is getting challenged because I told about the thing in this lecture that how this impacting the circuit, and for every IC what we are doing that we are designing a separate EST protection device. So there is not at all any EST CAD available in the industry. Somebody can also work on the EST computer aided design where they can incorporate the high current breakdown models on this, and they can use for a given IC what device has to be used. They can keep that. EST protection device is an art. It is not only about the thing that only that I design device. It will work very properly. It has to be very much tested under in the industry also. It cannot only be done by the simulation. You will get a result. You will not see that. You have to manufacture IC and you have to test the EST pad. Then you can tell that my design is better than others. Then you have a device meter are useful in design process. For that is that for the TCAD is being used for the ESD circuit or device design. Okay, so other thing also we have covered here methodology for bandwidth improvement of LVDS driver is explained in this thing. Issue device statistics is studied in this lecture, and this is yes increment improves the device robustness, and a marginal increment in this leads to the bit down scaling. So these are the things we have taken it from the this lecture. The future aspects, this thing you can work on your, if you want to pursue a PhD or any higher studies, you can work on the device robustness improvement using various parameters, receiver end performance improvements, impedance mismatch at receiver end, and development of the complete CAD flow for the optimization. Because does not exist any CAD flow, you can work on this also. Okay. So any question from your side? Any question from your side?
So
Any audience? Any question?
I would like to request participants to raise a few questions.
If anybody can ask the question, they can ask. So I hope there is no question. So I can ask the question from your side, from my side.
Yes, sir, you can ask.
What can anybody tell about the what is the EST phenomenon? Why it is important in the VLSI? No. So okay. Thank you very much for joining me.
So I would like to convey my gratitude to Professor Dheeraj Kumar Sinha sir. So he has given an informative lecture on the topic of ESD failures. So we are looking forward for more cooperation from him regarding analog design circuit as well as VLSI circuits. Thank you, sir.
Thank you. Thank you.